Hey everyone, hope you're all doing well. Before we get into the details of this video, take a look at the room around you and try to estimate what is the width of the room that you're in. So just look around you for a second and try to make an estimate. Maybe you're in a room where the width is around, say, 12 feet or something, or maybe you're in a larger auditorium and the width of the room would be 20 meters or something like that. But just try to make a quick estimate. And once you've done that, look at the device that you are watching this on. Maybe you're watching this on a smartphone or on a laptop or computer, and try to estimate what is the mass of that device that you're using. So if it's a smartphone, maybe around 20 grams, 200 grams, something like that as a mass for the phone. And then maybe ask yourself, what is your estimate for how long have I been asking you to estimate random quantities? Maybe 45 seconds or something like that. Okay. The point that I want to make with these estimates is when we are trying to quantify different sorts of physical measurements, we have to include identifications of what type of quantity are we using and what units are we using to describe that measurement. If I said the width of the room that I'm in is 10, well, 10 what? 10 inches, 10 miles, we need to have units identifying what kinds of quantities are we using and what are the units that we are using to compare that particular measurement to. So that's what we're going to be talking about for this video, the different types of physical quantities, the units that we use to describe those quantities, how we do different kinds of operations with different kinds of physical measurements, and also how we can use the properties of what kinds of units we're using, what kinds of physical measurements we're looking at, to identify what potential equations could describe how these physical properties are related to each other. Okay. So let's start by looking at just the base metric quantities, the base SI quantities that are used in the metric system. So these are things like time, length, mass, electric current, thermodynamic temperature, the amount of substances, and the luminous intensity of an object. These are the 7 base quantities that, for the metric system, all other quantities are based on. Okay? So for example, for time, I'm going to use these square brackets to denote the dimension of the quantity. So times are going to be capital T, lengths are going to be capital L, masses, electric currents, so on and so forth. That's what I'm going to use the square brackets for. And in the metric system, we have kind of our generally used assumed unit for these. So times are generally going to be measured in seconds. Lengths are generally going to be measured in meters. Masses are going to be measured in kilograms, so on and so forth. Okay. And all other quantities, all other physical quantities that we look at in physics are derived from, or can be derived from, these 7 quantities. We could have used other combinations of units as our base kind of starting point for describing all of these other kinds of units, but these ones were the ones that were particularly selected. And since 2019, all of these base SI units are no longer fixed to physical artifacts. Like there used to be a bar that defined this is how long a meter is. We're no longer basing these SI units on physical artifacts, but instead they're exactly fixed to physical constants or exact definitions. So anyone could, instead of having to reference what is this particular bar that is stored somewhere, what is the length of that bar for a meter, scientists can actually compare this with specific physical measurements. For example, 1 second is defined by a particular transition in cesium atoms and saying how long does it take to go through exactly 9,192,631,770 transitions of this particular atom going through this particular transition. So people can go and measure that themselves and say, okay, this is how we have now defined what a second is. So we're not going to go into the full details of how we've defined each of these things. That might be the topic of a future video, but we want to see how do we actually use these different quantities, what does this tell us about the types of measurements that are being made, and how can we use this to check for potential issues with proposed equations. So again, those 7 base SI quantities, there are lots of other kinds of measurements out there, but we can describe all of those other measurements and the types of quantities that we're dealing with in terms of those 7 base quantities. For example, when we talk about speed, we talk about that in some kind of length divided by some kind of time. This could be meters per second, miles per hour, I don't know, cubits per fortnight. We can have some kind of length divided by some kind of time. Again, for the metric system, the assumption is going to be that we're generally going to be using meters per second as our default measurement. If we instead look at acceleration, well, we're going to see how acceleration is a length divided by a time squared. The generally assumed metric version of this is going to be meters per second squared. Again, we're going to actually find evidence backing this up in the next video, a testing physics video. Force, well, that's going to be a mass times a length divided by a time squared. And for force specifically, we actually come up with a new definition, what we call a Newton of force. And 1 Newton of force is defined as 1 kilogram times a meter divided by a second squared. Okay. So again, these new units, for example, newtons, we can define those in terms of our base SI quantities. Similarly, when we talk about joules of energy, or watts of power, or Teslas of magnetic field strength, we can describe those in terms of these base SI units and these different dimensions that we've defined here, these kind of base dimensions. So how do we use these different kinds of quantities? Well, if I'm adding or subtracting or comparing any physical quantities, they have to have the same dimension. If they don't have the same dimension, there is no way to add them, subtract them, or compare them in any kind of coherent way. So for example, if I have what is 5 kilograms plus 8 seconds, those cannot be combined. It's just a nonsense statement. I'm looking at a mass and a time, and if I'm trying to add those or subtract those or even compare those, I can't say, is 5 kilograms larger than, equal to, or smaller than 8 seconds? Well, that's kind of a nonsense comparison. We just can't compare those particular values. Okay? So again, if I want to actually go through the operations of adding, subtracting, or comparing values, they have to have not only the same dimensions, but also the same units. And this might include converting between different kinds of units of the same kind of quantity. For example, when we talk about lengths, I can talk about lengths in terms of meters or feet or yards or miles or inches or, centimeters, millimeters, kilometers, all of the SI prefix meters quantities. All of those are lengths, but if I want to actually do a comparison or add or subtract these quantities, I want them to be in the same units as well. So let's say I have 5 kilometers plus 8 miles. Right now, they're both units of length, so I can do something with this, but I can't complete the addition right now because, well, would I get 13 what exactly? So if I want to actually perform this operation, I have to go through a unit conversion. So let's say that 1 mile is approximately 1.61 kilometers. In order to do this operation, I would have to be able to convert that 8 miles to some number of kilometers. And there's a variety of different ways that you can kind of organize this. If you have a preferred method of how to do a unit conversion, that's great as long as it's a reliable method. I kind of like putting in these conversion factors where I'm using either 1 mile over 1.61 kilometers or 1.61 kilometers over 1 mile. And the goal is I want to cancel out the units that I don't want and replace them with the units that I do want. So if I have miles, then I want to divide by something with miles in this conversion factor, so those miles will cancel out. So we've got miles in the being multiplied and divided. They're just going to cancel out. And if I do 8 times 1.61, you'll get 12.88, and the only units that are left are kilometers. So after this, we can say, well, 5 kilometers plus 8 miles is the same as 5 kilometers plus 12.88 kilometers to give us 17.88 kilometers. Again, this is a fairly introductory version to doing unit conversions, but still hopefully a good reminder for everyone. Okay. But what if I'm instead multiplying or dividing quantities? So he said if I'm adding, subtracting, or comparing quantities, they have to have the same units. They have to have the same dimensions in units. If I'm multiplying or dividing quantities, the units that you get, the dimensions of the resulting quantity that you get, those dimensions and units are also going to be multiplied and divided. So let's look at some examples of that. If we're looking at a speed, we're saying speed is defined as how far did you travel, what is the distance that you traveled, divided by how long did that take. So it's a distance divided by a time if we want to get a speed from that. Well, that means the dimensions of speed is going to be some kind of length, the dimensions of distance, divided by some kind of time. Again, this could be meters per second or miles per hour or any length divided by a time, but that's the dimensions that speed is going to have. The units, again, it could be meters per second, miles per hour, any combinations where it's a length divided by a time. What if we're looking at a volume? So let's say I have a rectangular box, and I want to know what is the volume of that box. Well, volume of a rectangular box would be length times width times height. And each of those, the length is a length, obviously. The width is also a length. The height is a length. So the dimensions of volume would be length cubed. This could be cubic meters or cubic feet or cubic inches, cubic centimeters, but it's going to be some kind of length cubed in order to get those correct units of volume. If I looked at something trickier like angular momentum, the angular momentum of a point particle around some given axis, so if we choose an axis and we have some particle moving in some way, it's going to be what is the distance from the point that we're measuring the angular momentum around to where that particle is, crossed with the momentum of that particle. And the momentum is mass times velocity. So if I want to know what are the dimensions, what kind of a quantity is this angular momentum, well, that r distance, that's going to be a length, and our momentum is a mass times a velocity. And we said velocity was a length divided by a time. So if I combine these together, that's going to be a mass times a length squared divided by a time. That would be the combination of dimensions that give us these dimensions for angular momentum. For other kinds of operations, let's say I'm taking a derivative. So this is going to be a little bit of calculus, but we're just looking at this in terms of the units. So let's say I'm taking a derivative of one quantity with respect to another quantity. Well, in that case, I'm going to divide the dimension. I'm going to take that original quantity and divide by the dimension of the variable that the derivative is with respect to. So for example, acceleration. Acceleration is the time derivative of velocity. It's the rate of change of velocity. How is my velocity changing with time? Well, if it's that derivative, the dimensions are going to be the dimensions associated with velocity, so a length divided by a time, divided by the dimensions of the variable that you're taking the differentiation with respect to. In this case, we're taking the derivative with respect to time. So we have to divide by another time. So overall, these dimensions for acceleration are going to be a length divided by a time squared. Again, generally, we're going to be using metric units, so it's going to be a meter per second, a meter per second squared for the units of our acceleration. If I'm taking an integral with respect to a quantity, then I'm going to be multiplying by the dimensions of the variable the quantity is being integrated over. So for example, the definition of work is how is force integrated over changes in position. So I'm saying how much force is being applied, and I'm adding up, when I'm doing this integration, I'm adding up the force times all of these little changes in position, and then I'm adding up all of those particular effects to get that full total amount of work done. Well, our dimensions of force, we said that's a mass times a length divided by a time squared. We said a Newton was a kilogram meter per second squared. So those are our units of force. But we're integrating this over changes in position. We're integrating this over a distance, a length. So the units for work are going to be a mass times a length squared divided by a time squared. Okay. The general definition of this, the general metric units are going to be kilograms times meter squared over second squared, and we call that a joule. Again, this is another one of those derived quantities. So again, we can perform these different kinds of operations and look at what are the dimensions and the units of the quantities that would come out on the other side of this when we multiply, divide, take a derivative, take an integral, when we perform mathematical operations on some of these different kinds of quantities. And this actually gives us some really, really helpful tools. Because if I have any equation that's relating physical quantities, so I have some combination of physical quantities over here, and I've got another combination of different physical quantities over here, and I'm saying I can equate those with each other. Say, force equals mass times acceleration, or a certain kind of energy has these particular values. In any of these equations, the dimensions on either side of the equation must match up. If I'm saying that these things are equal to each other, they must have the same dimension. Otherwise, I'd be saying something literally nonsensical like, oh, my mass is 30 meters per second. That's a nonsense statement. The dimensions have to match if we're going to be comparing quantities. And let's check this in a couple of examples. So this is one of the constant acceleration equations. If I have an acceleration, little a, that is the same magnitude the whole time, and also the same direction the whole time, then I can find what is my position at different times going to be given my initial position and my initial velocity. So this is my final position at some time is equal to my initial position plus my initial velocity times how much time has passed, plus 1/2 times that constant acceleration times the time squared. Again, if we are adding, subtracting, or comparing quantities, the dimensions of all of those quantities must match up with each other. So all of these quantities, all of these terms must have the same dimensions. Let's check this. Well, my final position, that's going to be a length, some kind of distance. Where am I? Okay, so that's going to be a length. So everything else also has to end up as a length. Well, my initial position, cool, that's also a length. Pretty straightforward. This middle term, initial velocity times time. Well, velocity is a length divided by a time, and I'm multiplying that by a time. So those times are going to cancel out, and I'm left with just length. This last term, the 1/2 acceleration times time squared. Well, acceleration is a length divided by a time squared, and we're multiplying that by a time squared. So the t squareds cancel out, and this whole term overall still gives me a length. So all of those terms are just units of length when we go through these different operations. Okay? So this is an example of how any physical equation, if I'm relating different physical quantities, the units, the dimensions of those quantities must match up on either side of the equation. Let's look at some other examples. So different types of energy. Well, we talked about work, how work is the integral of force over displacement. And so the dimensions of that work are a mass times a length squared divided by a time squared. And you can think of work as the amount of energy that's either being added to a system, if it's positive, or the amount of energy that's being removed from a system, if it's negative. So if that's an energy, all other kinds of energy must have these same dimensions. Well, let's look at kinetic energy. The equation for kinetic energy is 1/2 mv squared. So we've got the dimensions are going to be 1/2 doesn't have any dimensions, so you don't worry about that one. Mass is just a mass. Velocity is a length divided by a time, but we're squaring that velocity. So both the length is going to be squared and the time is going to be squared. So we get mass times length squared divided by time squared, matching our dimensions for work. What about gravitational energy? If I'm on or near the Earth, the gravitational energy is the mass of the object. If I have some object that I'm moving around to different locations, the gravitational energy is the mass of the object times the gravitational acceleration at this location on the Earth, so 9.8 meters per second squared if you're at most locations on or near the Earth. And y is just how high up in the air is the object situated. Well, the mass is just m. Little g has units of length, has dimensions of length divided by time squared, and we multiply that by another length. So when I multiply these two lengths together, I'm going to get mass times length squared divided by time squared. Again, matching our definition of work. One more of these, the spring potential energy. Well, the equation for spring potential energy is 1/2 kx squared, where k is the spring constant in newtons per meter. Okay? So the units, the dimensions of newtons divided by the dimension of length. A newton, remember, a newton is a mass times a length divided by a time squared. So if I do this newtons divided by length, so mass times length divided by time squared divided by length, well, those lengths are going to cancel each other out. So just this part here is a mass divided by a time squared, and then we're multiplying that by a length squared. A mass times a length squared divided by a time squared. All of these have the same dimensions, so we can check this to make sure that any of these equations, if they're talking about the same type of quantity, they must have the same dimensions. We can actually use this to our advantage. When we're going through a physical equation, if we're keeping track of the dimensions and the units of the quantities that we end up with, we can use this as a sanity check, because if the dimensions don't match at the end of the problem, the equation that we derived cannot be correct. Because again, then you'd be comparing completely different kinds of things. If I say, oh, 12 kilograms is equal to 3 meters per second, that can't possibly be correct. So let's look at a concrete example of this. Suppose I release a cart from the top of a frictionless ramp of length L. So let's say I've got this ramp, let me go this way. I've got this frictionless ramp and there's a cart on it. We're going to call this position 0. And that cart is going to go down this frictionless ramp and reach the bottom of this ramp, which is, let's say that's position L. And it does that in a certain time t. And I want to know, what is the acceleration of the cart during this motion down the ramp? Well, we kind of already introduced this equation saying if I have a constant acceleration, I can relate the final position to initial position, initial velocity and time, and the acceleration. So in this case, for my ramp, we're saying, I'm going to say that we're starting from position 0. So my initial position is 0. And we're releasing this from rest. So my initial velocity is 0. So in this case, those two terms, they just go to 0. I'm starting from position 0, and I'm starting with 0 velocity. At the bottom of the ramp, we're saying, oh, it's gone a distance L. So that's our final position. We're assuming that we measured the time it takes to go down that ramp. So we have the time, and we're trying to find out what is this constant acceleration. Well, I can do a little bit of algebra and rearrange this, and we get that the acceleration is 2 times the length of the ramp divided by the time it took to go down the ramp squared. Again, this is in the case where we are assuming that we're starting from position 0 and we are starting with the cart at rest. We're just releasing the cart from rest. And if this is right, if this has the opportunity to be right, then the dimensions on either side of this equation still have to match up. Well, when we check this, acceleration, those units should be a length divided by a time squared. And when we look at this combination of terms, we get a length divided by a time squared. So this matches, and it has passed this particular test. If we got something different, if we didn't include that t squared and said acceleration is just a length divided by a time, those units would not match. And it would immediately identify that we've made some kind of math typo. The dimensions aren't working out. We're comparing not only like apples and oranges, but like comparing apples to the concept of music, something completely different where we can't make any comparison between those whatsoever. Another helpful thing that this dimensional analysis allows us to do is if we have a physical equation, and let's say we forget what are the units of some particular quantity, we can use that physical equation to derive what those dimensions have to be. Let's look at an example of this. So for Newtonian gravity, Newton's model of gravity is that the gravitational force, if I have two masses, mass 1 and mass 2, that are a certain distance r away from each other, so the centers of these spherical masses are a distance r away from each other, that gravitational force should be equal to Newton's gravitational constant, this capital G value, it's just a constant value, times the product of the masses divided by the distance between those masses squared. Okay. So if I change the values of those masses, or if I move those masses closer together or further apart, this allows us to calculate what is the strength of that force of gravity. But this value of G, this capital G, what dimensions does it have? What kind of dimensions or units does it have? Well, for the gravitational force, for any force, that's got to be a mass times a length divided by a time squared, kilograms, meters per second squared. That means whatever the dimensions of G are, if I multiply that by two masses, so we get mass squared, and divide that by a distance squared, a length squared, we can rearrange this and figure out what the dimensions of G are supposed to be. Notice I can rearrange this by multiplying L squared to both sides. So we're going to get an L cubed on this side. And I can divide both sides by a mass squared. So it's going to cancel out this mass and leave one more mass in the bottom. And we get the dimensions of this gravitational constant have to be the length cubed divided by a mass multiplied by time squared. It's really weird units, but we're actually going to go through some other descriptions of how we can actually check this and experimentally verify that these particular dimensions and these particular units actually do work out in real experiments and real situations. So again, we're going to be doing some tests on this, looking at the dimensions of different kinds of quantities. I'm going to be putting some videos up for multiple different ways, for I think 2 different ways of actually measuring the value of little g, the local gravitational acceleration, including the units. And we'll also go into more details on some helpful tools in dimensional analysis, how you can use this to estimate different quantities. So that's going to be coming up in a couple of videos that are going to be coming up pretty soon. If you have comments or questions, please throw those into the comment section. And that's it for this video, so have a good rest of your day.